Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discussing about the reaction of the naphthalene, and the last reaction we have described reduction reaction. How naphthalene can be reduced in a different way by using as a proper reagent and maintaining the proper reaction condition. How one can reduce that naphthalene into the desired products that you can see over here. So here is a naphthalene. I have represented here on the blackboard naphthalene, and there are the three different ways. Here two hydrogen means when the sodium metal is kept when it is treated with that ethanol, there is a nascent hydrogen atom is generated, and that nascent hydrogen is responsible for the reduction of that naphthalene. Partially reduction can be carried out, and we will get the yield 1,4-dihydronaphthalene. So that is one of the product. Another way of when sodium metal is with isopropyl alcohol, like only the alcohols is combination is changed and the temperature. In a previous case the temperature is kept around 78 degrees centigrade, whereas in the second case they raised the temperature around 132 degrees centigrade, and what they found, what they got 1, 2, 3, 4 tetrahydronaphthalene. Look at 1, 2, 3 and 4. There is a CH2 group, and that type of the compound is called as a 1, 2, 3, 4 tetrahydronaphthalene. So that is one of the ring is completely saturated and one of the ring is remains as it is benzene. As we know that benzene is aromatic in nature. Now look at the next one, that is the reagent is changed over there. H2 in presence of the molecular hydrogen in presence of nickel or platinum. What do you get? All the double bond get converted into as a single bond, means we are getting the desired product, that is a decalene, that is a saturated compound. So aromatic we will get completely as a non-aromatic compound. So or we can call it as a aliphatic compound. Decalene is a two ring fused together and we got this compound. So completely saturated. These are the reduction, as I already mentioned you, are reduction in terms of the organic chemistry. There is a addition of hydrogen atom, that is called as a reduction. It is exactly opposite to the oxidation reaction. Oxidation means removal of hydrogen from the starting material or the substrate is known as a oxidation, and before that we already discussed all these cases. So these were the discussion we have discussed in our previous lecture, and today what we are going to discuss. So today we are going to discuss about the next polynuclear compound, which is anthracene. And as we know that anthracene similar to as a naphthalene, we know that naphthalene, the two benzene rings fuse together leading to the compounds known as naphthalene, where two two aromatic rings are fused, they are sharing two carbon atom for bond forming and getting that compound. So let us see, second one is anthracene. Anthracene, that is this is a second polynuclear aromatic compound we are talking, because generally aromatic compounds are further divided into as a two type. One is a polynuclear and another one is a heteronuclear aromatic compound. Polynuclear means the rings, many rings, which is made up of by carbon atom, means there is a involvement of only and only carbon atom. Then we can call it as a polynuclear, or you can call it as a polycyclic aromatic compound. They possess, they shows all the important characteristic feature of aromatic character, as we know that aromatic compound are fully conjugated, planar, cyclic system containing 4n plus 2 pi electron are known as aromatic compound. Along with they possess all the characteristic of whatever we have described during that aromatic character and Buckel rule, all are following that one. So here anthracene is a tricyclic, naphthalene is a two cycles are fused together, two cycles are present, but here the tricyclic means three cycles are present. Anthracene is a tricyclic aromatic hydrocarbons. Hydrocarbon word itself suggests that the organic compound which is made up of by carbon and hydrogen is known as a hydrocarbon, in which three benzene rings are fused together in a linear manner, and its molecular formula is C14H10. C14H10. Its molecular formula is a C14H10. And this is a molecular formula, it is a tricyclic. Three benzene rings are fused together in a linear manner. Now let us see occurrence, where it is occurred. That little bit we are talking about the occurrence. Anthracene also present in coal tar, a mixture of organic substances formed when coal is converted into coke by heating at high temperature about 1000 degrees centigrade in absence of air. So that is the occurrence we have seen. And who synthesized anthracene first time in the laboratory? Similar to as a naphthalene, we have described naphthalene is how naphthalene is synthesized in the laboratory is known by Haworth synthesis or Haworth synthesis of naphthalene. What he did, how Haworth prepared or synthesized that compound, what are the starting material he had taken, and how he obtained that product, that if you Can you recall the starting material he has taken as a benzene along with succinic anhydride treated with in presence of Lewis acid catalyst, generally AlCl3, aluminum chloride, Friedel-Crafts acylation reaction, that is one of the famous reaction takes place, and there is a substitution of that group attached, and after that when we got that product or the intermediate, it is further treated with Clemmensen reduction. As we know that it is a very good reducing reagent which can reduce carbonyl group into as a hydrocarbon, and after getting that hydrocarbon, that intermediate further treated with the cyclization can be carried out with by addition of HF, hydrogen fluoride, which is known for the cyclization. The cyclization can be carried out to get alpha tetraquinone type of the compound, tetranone type of the compound, and after that again the Clemmensen reduction use once again, and essentially you will get the product, desired product, that is a tetraline type of the product we are getting. Generally that is a tetrahydronaphthalene 1 2 3 4 tetrahydronaphthalene type of the compound getting, and then to bring the aromatization, finally that compound treated with selenium or palladium in presence of charcoal. After heating we will get the desired product, that is a naphthalene. This is the very famous reaction, that is the Haworth synthesis of naphthalene. Similarly here Haworth synthesis of anthracene. Let us discuss about how anthracene can be prepared in the laboratory, and as we know that the structure of naphthalene will be this one. This is a structure of 3 benzene ring fused together, and this is the structure of anthracene. I have just shown on the blackboard. Now how do we prepare, how do we synthesize this compound in the laboratory? What are the starting material? And for that purpose you must follow the Haworth synthesis of anthracene. So here I am writing that one, Haworth synthesis of anthracene. Haworth synthesis of anthracene. What he had taken as a starting material, he has taken as a benzene once again, and this benzene would be treated with, this is a compound which I am showing over here. You are familiar with this compound, I think. This is the starting compound, which is benzene, and this is a phthalic anhydride. This is a phthalic anhydride. hydride, and the reaction once again carried out with Friedel-Crafts oscillation reaction in presence of Lewis acid, which is AlCl3. That is as we know that it is a Lewis acid catalyst, this one. So it will speed up the reaction. If reaction are not carried out, then little amount of the catalyst is used. The catalyst in the organic chemistry playing very important role. It will speed up the rate of reaction, so that product should be kinetically more favorable, or we can say kinetically controlled reactions, and with high yielding product we are generally obtain. Now, so what do you get? This benzene ring is going to attack over there, and that get open like this. So the as we know that mechanism in the organic chemistry or detailed study of sequence of steps which are involved in the conversion of reactant into product is known as a mechanism. That is a definition of the mechanism, and according to that, so it is attacking on that carbonyl group, so it get open like this, and you get the compound with this one. It's a compound which you are going to get. It's a benzene ring. I am not going to show that here, but when this attached to this carbonyl group remains there, further this is a benzene ring I am showing over here, and other part at this position is a carbonyl group, and here hydroxy group is attacking. So this is the compound which we are going to get over here, and after that what, then you can use the catalyst Zn Hg in presence of HCl, which is a Clemmensen reduction. This one Clemmensen reduction. What the Clemmensen reduction? Generally, suppose you have a group C double bond O R, and Clemmensen reduction carried out, we are going to get RCH2R like this. Means carbonyl group is get converted into as a hydrocarbon. That is the speciality of that Clemmensen reduction, and therefore we are going to get here the product, this one. So you can write benzene ring as it is, here CH2, then this benzene ring remains as it is, and here this is a acid group at a proper position. And now you cyclization HF, we know that it is a reagent known for cyclization if there is acid, and this type of the aromatic compounds are in a proper orientation. Cyclization can be carried out, and we will get the product which I am going to show over here. See here the product which you are going to get over here, this one C double bond O, this the aromatic compound on this side, it remains as it. Now look at this carbonyl group. Once again you can use here whatever the reagent we are using, zinc amalgam in presence of the HCl, you can use once again here ZnHg, zinc amalgam in presence of HCl, which is known as a Clemmensen reduction. Clemmensen reduction. After doing that, what you are going to get? You are going to get your desired product, as we know that, and it's very simple. Here you are going to get is your desired product. Look at this one. So this is nothing but as an anthracene. Yeah? Anthracene, that is a product which, and this synthesis is known as a Haworth synthesis of anthracene. What he did, he took the starting material which is readily available, benzene and the phthalic anhydride, and phthalic anhydride would be obtained from phthalic acid heated at high temperature in presence of aluminum oxide. You may get as a phthalic anhydride, and which is utilized for the synthesis of naphthalene, as you can see over here. Benzene as a starting material, phthalic anhydride. This is a well-known reaction, Friedel-Crafts acylation reaction, and it requires AlCl3, which is a Lewis acid catalyst. Catalyst will speed up the reaction, and this is the compound which we are getting here as an intermediate, and preferentially or exclusively he carried out the reaction with ZnHg in presence of the HCl. This is one of the famous reducing reagent, that is a Clemmensen reduction. According to that, it get reduced, and they got this an intermediate. When these this acid group in at a proper orientation, then HF is used as a cyclizing agent. Cyclization carried out, we will get this type of the intermediate, and finally we will get the desired we after the Clemmensen reduction we will not get this one. Let me, here we are going to get this type of the product, and after this product further it is treated with selenium or palladium in presence of charcoal heated, and you will get the compound, the desired product, that is a naphthalene. So let me draw here properly. This is aromatization, because here is not the aromatization. After the Clemmensen reduction, it reduces only this carbonyl group into as a hydrocarbon. Still two rings are the aromatic, middle one is not the aromatic, and therefore here the aromatization is brought by using the proper reagent, selenium, either selenium or palladium in presence of charcoal heating. It produces or it gives the compound which is nothing but as an anthracene. So this is the structure which we got here, is an anthracene. Anthracene, that is a product which we got over here. So look at this. This is a very simple synthesis for anthracene, and the resonance energy of anthracene is 84 kilocalorie per mole, that is 28 kilocalorie per mole per ring, and this stabilization energy is lower than that of benzene. Benzene, as we know that stabilization energy for benzene 36 kilocalorie per mole, but here in this case anthracene is only 28 kilocalorie per mole, and that is why Anthracene is much less aromatic than benzene and gives both the substitution and addition reaction with ease. We know that benzene is an aromatic compound. The main characteristic reaction of aromatic compounds, especially benzene, it undergoes electrophilic substitution reaction, as well as in special condition it shows as a nucleophilic substitution reaction. But here anthracene, even though it is an aromatic compound, and that benzene, remember, do you remember benzene cannot undergo addition reaction? Why benzene do not undergo addition reaction? If it undergoes addition reaction similar to alkene and alkyne, it loses its aromaticity, means stability is disturbed, and therefore benzene do not undergoes addition reaction like alkene and alkyne. Instead, preferentially or exclusively it undergoes as a electrophilic substitution reaction more readily. In a special condition or in a forceful condition, benzene undergoes nucleophilic substitution reaction. But here anthracene is a less aromatic than the benzene, and therefore remember the difference between benzene and the anthracene. Anthracene is aromatic in nature, no doubt about it, but the aromaticity of that benzene is less as compared to the naphthalene, because they differ in energies. Stabilization energy of benzene is very high, 36 kilocalorie per mole, that is called as the resonance energy or the stabilization energy. But in case of the anthracene, there is only 28 kilocalorie per mole, and therefore it is a aromatic but less aromatic than the benzene, and therefore some differences in the behavior of anthracene. Anthracene can undergoes substitution reaction, electrophilic substitution reaction, as well as addition reactions very easily. So the reactions of anthracene, what kind of the reaction? Anthracene commonly undergoes aromatic electrophilic substitution reaction, radical substitution, and 4+2 cycloaddition reactions. Ninth position of anthracene is more reactive because of stabilization of sigma complexes. These are the some of the point which we are going to discuss in our upcoming lectures, and still then I think whatever the discussion we discussed today, main focus on that anthracene along while studying as a reaction, how number systems are utilized in anthracene, that also we are going to discuss in our next lectures. Why 9 position is more reactive? What is 4+2 cycloaddition reaction? It is a photochemical reaction. what do you mean by, how do you define 4+2 cycloaddition reaction, and dyne and dienophile, that also the term we will discuss in our upcoming lectures. Till then, have a nice day. Thank you.